All right, pre-calculus, we're going to do logarithms, day 2. Here are, I think we talked about this in class yesterday, but here are two particularly important bases for logarithms. The base e and the base 10. This is about e, this is about 10. The number e, which again is approximately 2.718, we saw that in the notes a couple of sections ago. It shows up so often as a base in the study of growth rates with exponential functions, like with bacteria or populations, finances, and stuff, that we have a special designation for a log with the base of e as the inverse of that exponential function. And it is called the natural logarithm, because things in nature grow continuously, and we use e, a equals p times e to the rt. We use e as the base of the exponent when things grow continuously. Okay, so y is equal to the natural log of x if and only if x is equal to e to the y. Now you got to understand, this means the log base e of x. That's what that means. The natural log is the log with the base of e. So if I rewrite it, e is the base of the log, so it's the base of the exponent. These two switch places. Okay. The number 10 was historically used frequently as a base for logarithms, because before they had calculators, people had to use charts in order to evaluate a logarithm. Somebody had done lots of logarithms with the base 10 and made a whole bunch of charts, so people would just look up the number. Since the most readily available chart was for a logarithm with a base of 10, we have a special designation with a log of base of 10. It is called the common logarithm. Okay, and so the common logarithm goes like this: y equals log of x. I don't even bother writing a base down there. That's when it's assumed that you know I'm talking about log base 10. That's going to be true if and only if 10 to the y is equal to x. So basically I wrote the logarithm and then I wrote it in exponential form. Okay, so I think you had a homework problem like this last night. Find the domain of this function. Okay, it's a logarithm, so it's going to have a vertical asymptote, and it's moved 2 to the right. Now instead of being a vertical asymptote on the y-axis, I'm going to move it 2 to the right. So I'm going to put a vertical asymptote at x equals 2. Or you can think of it this way. This x minus 2, that's supposed to be greater than 0. Whatever you have in the log function, it's supposed to be greater than 0. So x minus 2 is supposed to be greater than 0. So add 2, and the domain is 2 up to positive infinity. Just like here we can see, it's going to be 2 up to positive infinity. We're supposed to graph the function. Okay, well, if I move the asymptote 2, the point 1, 0 moves 2, and it's at 3, 0. Now a log function would stay on the right side of this vertical asymptote. It would go up, and it would go through this point and then take a right. However, this has got a negative in front of it, so it's going to flip. So this is going to stay on the right side up here, come down, go through this, and then take a right underneath the x-axis. If I really wanted to, I could see about finding another point to go through, but I think you guys get the idea. Is f a one-to-one function? Yep, it passes a horizontal line test, so its inverse will pass a vertical line test. Determine the range of our function. Well, I use all the positives, and although this goes slowly, it will continue to go down so that I use all the negatives. This is negative infinity to positive infinity. Give the vertical asymptote, it's right there, x equals 2. And then here we go, just for fun, we're going to find and graph the inverse. Well, to find an inverse, you switch x and y. So here's, I'm going to write this what it is. Y equals negative natural log of x minus 2. Here's the inverse. I'll put a little asterisk saying, hey, this is where I did my work. It's going to go x equals negative natural log of y minus 2. I want to get y by itself. So I'm going to get rid of this and call this negative x is equal to the log base e of y minus 2. You know that natural log has a base of e, and then I'm just going to rewrite this. So it goes e to the negative x is equal to y minus 2, and then the last thing I'm going to do is add 2. So y equals e to the negative x plus 2. There's my inverse, and I'm supposed to graph the inverse. I could try to reflect this over the line y equals x, but that's going to be weird for me to do since this crosses that line. So look, I'm just going to graph this. E to the x looks like this. It's got a plus 2, which means it goes up 2. Now, when I have exponential functions, they have a horizontal asymptote. So this is going to go up 2, and this will be my horizontal asymptote at y equals 2. The 0.01 for the exponential function will become the 0.03. And then this is a negative x. It's a negative x, so it's going to be an exponential decay. It won't be an exponential growth. It'll be exponential decay. Okay, so watch this. Comes down this way, hits this, and then it goes along this line right here. And now you can see that it is actually a reflection over the line y equals x. Now if I'm supposed to give the domain and range, don't even think of looking at this picture and trying to figure it out. If this is an inverse, you switch these. The domain was 2 up to infinity, so the range will be 2 up to infinity. And the domain, the range was negative infinity to positive infinity, so the domain is negative infinity to positive infinity. There you go. Go to the next page.